The purpose of this video is to describe distributed database management systems, to discuss client-server systems, to examine different ways databases are accessed on the web, to discuss XML and related document specification standards, to define the data warehouses and explain their structure and access, and also discuss the general concepts of object-oriented DBMSs. So far, we've only used databases that exist at one location. We have Microsoft Access or Microsoft SQL Server or MySQL or some other system like that, and we only use it on one computer. But in reality, what we want to do is we want these databases to be at multiple locations. And so what we're going to do is we're going to use our typical network communications, such as TCP/IP and HTTP, to be able to have this data at different locations. Now we can have what's called a distributed database, which is going to be a single logical database that is physically divided among multiple network computers. So in reality, what happens is I can have a database that when I look at the data in it, it looks like it's all in one location, but in reality, it's actually distributed and it's in different places on the web, or even just in our local area network. Now we need to use what's called a distributed database management system, or a DDBMS, to be able to do this. Now essentially the way this works is we have a database at each location, and what happens is the database is actually replicated from one location to the other, and then the two databases are responsible for maintaining a list of all of the transactions and records, so that way users at either location do not realize that they're not using a local database. To do this, we're going to use what's called messages. Now a message is going to be, instead of a typical HTTP or TCP/IP transaction, we're going to use those as a transport mechanism, but what happens is when the packet gets to the receiving computer, it goes into what's called a message queue, or an MQ. And so what happens is the message goes into essentially an inbox on the database server, and then the database server is going to pick that message up, and then it will do whatever the transaction is that's on that piece of paper or that message, and then it does the particular transaction, and then it puts the results of it into an outgoing, or what's called an out queue, so basically like an out box, and then the computer that actually submitted the request is responsible for checking the out queue to make sure that their packet shows up. Now what happens is there's going to be a little bit of a delay, because what happens is every single packet that we send to the server, sorry, not every single packet, but every single transaction that we send to the server goes in the form of a message. We submit the message to the in queue. The in queue has to basically queue up all the messages, and the database system is going to handle those one at a time. When it handles it, puts it in the out queue, when there is an increase in processing time for this. But what it does for us, though, is it makes it where we know that the messages get handled in the order that they should be applied. And then we also know that it is going to force the computers to wait their turn. Now there is going to be an amount of time that is calculated here, so you can actually figure out how much time there is, and you need to know the access delay plus the transmission rate and so forth. But essentially what I'm saying is that you need to know that there is going to be a delay, but every computer is going to receive approximately the same delay in those messages. Our distributed DBMS, we have different types. We have homogeneous, which means that we have the same local DBMS at each site, meaning each site is going to be using Microsoft SQL Server, or each site is going to use MySQL, or each site is using Oracle. We can also use a system that allows a heterogeneous DBMS, and essentially what that means is that we could be using Microsoft SQL Server at one location, we could use DBase in another location, we could use Oracle at another location, and all of them actually will work as one database system, but in reality, they're all different systems. Now, these are all going to have to share some characteristics that we refer to as location transparency, replication transparency, and fragmentation transparency. Location transparency just simply means that the database may or may not be at my local site, but as far as the end user is concerned, they don't know any different. So what happens is they submit a message to the database system. The database system may or may not be at their local location, and it doesn't matter. They don't know any different. All they do is they just simply have to tell the DBMS, here's my request. The DBMS does whatever it needs to behind the scenes The users have no clue where that packet's going, whether it's at the local location or somewhere else, and it will just automatically do whatever it needs to do. We also have replication transparency, which means that data from my location is going to be replicated to some other location, and as the end user, I should not know that this is going on. What happens is, behind the scenes, the DBMS has to keep track of all of the transactions that occur in all locations, and then it's responsible for replicating that data from one location to another so that way both locations have the same data. We also have what's called fragmentation transparency. Now, this is a little bit different. This is going to be, we're going to take the data and we're actually going to break it up into logical places, meaning if I have a business that has multiple locations, we're actually going to put a database server at each of the locations, and then we're going to make it where, based on some sort of criteria, the data is going to be stored at each individual location, but only the data for that location gets stored. Once again, fragmentation transparency is the user should have no clue that this is going on. So what happens is, for this fragmentation, what we're going to do is we're going to look at this table and we say, okay, we have a part number, we have a description, how many are on hand, what class it is, and what warehouse it's in. Now, these warehouses are physical, separate locations. So the question is, if this iron exists at warehouse number 3, where should it be? Should it be on a server that's sitting back at warehouse location number 1? And chances are, no, it shouldn't, because we're going to have a large number of transactions that occur at warehouse 3 that are all going to have to go across our data lines and going to cause the system to be slow. So instead, what we're going to do is we're going to break it up into fragments. And so what we're going to do is we're going to have a database server sitting at warehouse 1 that has only the records for warehouse 1. We have a separate database server at warehouse 2 that only has records for warehouse 2. And then the same thing, we have a third database server sitting at warehouse 3 that only has the records that apply to warehouse 3. What this does is makes it where when somebody sitting at warehouse 2 tries to look something up, they don't need to know that the data actually exists in their local location. But what happens is they're going to get that data back really fast because it exists in their local network, not going across the data lines. Now, in reality, if somebody sitting at location number 2 wants to check on the on-hand quantity of the dryers at warehouse 1, then they're going to experience a little bit of a delay because they're going to have to wait for that message to be sent across the data line, wait for the remote server to actually process the transaction, and then send the results back across the data line. Some of the advantages of having a distributed database is that we have local control of the data, meaning that I could have people at each location that are responsible for securing data for their own users. We're going to increase the capabilities of the system because we can use less resources at each location, and then we'll provide a better uptime so we have better system availability, and we'll also have improved performance. Each location pulls data from a local server rather than across the slow data lines. Disadvantages, though, you'll notice the list is longer here. The major thing is that we have to have a primary copy of our replicated data. And what that means is that we have what's called a master server. So one of our servers is responsible for being the main database server. It's the one that's responsible for making sure all the other servers have the data. It's responsible for making sure that the backups have occurred. It's responsible for being the point of contact for setting up user accounts and everything else. So we have one main server that is our fail point. And what happens is that one main server is brought down. This is kind of going to be like in the olden days with Windows, where if one of our domain controllers went down, then we had to wait for another one to get brought up as a master before anything else could work. This is still going on. It is a lot more complex query processing, which means that I have to know where the data is at. I have to specify in my particular server, these are your other servers. This is where you're supposed to look at for data. Now, the end user doesn't know that. The end user has no clue. But on the back end, we have to have all this set up ahead of time. We have some other problems with the concurrent update. When we talked about a deadlock before, we had 2 users trying to access the same data on the same server. Well, what if I have a user at one location trying to update a record and a user in another location trying to update that exact same record? Both of them are doing an update on their local server, The local server says, hey, this isn't locked, we'll let you do it. But then what happens is when they try to replicate the changes, there becomes a lock on the two systems. And so that particular record then has the chance of either getting corrupted, getting lost, or getting backed out completely. So what we're going to use is what's called two-phase commit. So one site acts as the coordinator. And what that means is that I have a main location that is responsible for telling the other server, yes, I approve that transaction. So what happens is user at the main location writes something to the database, user at second location writes something at the same time, and the main server commits the data. The second server says, hey, can I commit this data? And the main server says, no, somebody else just did. So now what happens is the second server has to go through a step-off process. It has to roll back the transaction and then reapply it, so that way we don't lose transactions in between. Our data dictionary also becomes much larger, and it also will become fragmented. So our data dictionary is going to be in our main location, all of our remote locations, and they all have to be kept up to date. So what happens is if we have indexes that are being applied and our remote locations are keeping track of their indexes, they also have to turn around and update the index at the main location. It is going to become a more complex database design, and we're going to have more complicated security and backup requirements. So how do we control which users can get into the system from which locations? What kind of information can they get into? Can they get into information from the other locations? And then also the backups, because we have to back up not only our main location, but also the remote sites. So there are some rules that have been developed for distributed databases. One of them says local autonomy, which means that each branch or each location has a server that has to be able to act independently should it lose a connection to the other servers. Now, if I've dealt with fragmentation, what that means is that I can only get to the data that's been fragmented for my server. So it's not complete autonomy, but it's enough to keep my one location up and running. We have no reliance on a central site. Now, this is not going to be true if we have a master that's responsible for coordinating our commits at multiple sites. We need to make sure that we have continuous operations, so all of our sites have to be up and running all the time. We have to have location, fragmentation, and then our replication transparency, so that way the users don't know that anything's going on behind the scenes. We need to make sure that whatever system we're using supports distributed query processing, which means that it has to be able to handle servers being at multiple locations. It also has to have what's called distributed transaction management, which means that the system has to support the ability to maintain these transactions and ensure that each transaction does not overwrite changes made by a previous transaction in another location. Our system should support hardware independence, which means that it should work on any platform. It should work on an Intel-based processor, AMD processor, anything else that's out there, and then also operating system independence. It should work on a Windows computer, Linux, Mac, and so forth, and we should be able to get our systems to work together. Network independence, this one's actually become less of a problem. Back about 15, 16 years ago, we had a problem where different networks use different network protocols. So if I were using an Apple server or Apple network, I had to use Apple Talk protocol. If I was using Novell, I had to use the Novell network. If I were using Windows, I had another one. And if I had Linux, I had TCP/IP to play with. So we had all these different systems. Well, nowadays, we're all going to be using TCP/IP as our common protocol for communications. We also need to be able to support different DBMSs. So if I'm using Microsoft SQL Server in one location and Oracle in another, the two of those should work together. Nowadays, most people use a database through the internet. And so the way that this works is you go to a web page, and the web server is responsible for creating these web pages on the fly. Think of going to Amazon or eBay or something like that. When you go from page to page on Amazon, you look at one product to the next product and so forth, there's not somebody there that is designing each page for you. What's going on is they have a template page that's responsible for performing a query, pulling data in from a database, and populating the data on the page. The part that most people don't realize is no matter what, the end user is always going to get an HTML document that is sent to them through HTTP as if it were a static page. The only difference is how is that page created. So you have static pages, somebody types out the code for it, and there you go, that's the page. A dynamic page that comes out of a database behind the scenes is going to be using some other programming language. So it's going to be something like ASP or PHP or C# or Java or Ruby or some programming language that is responsible for performing the query to the database, turning around, creating the HTML document, and sending it to the end user. Along with these HTML documents, we can also use what are called XML documents. Now, XML is not used to display information to users. XML is designed for transmitting data. So what happens is I have a Microsoft SQL Server DBMS that I want to get data into from, let's say, an IBM DB2 database server. Okay, now that's an old server that I want to be able to get data out of and pull it into Microsoft SQL Server. How can I get the data? Because the two of them actually don't talk. They cannot interface with each other directly. All right, so I have some options. I can get my data out of the DB2 server by exporting things into comma-separated value files. Oh, by the way, some of our values have commas in them. Oh, that breaks that. We could export things from DB2 into a tab delimited file. All right, that works unless we have any tabs and fields, which would break it. Or we can export things into XML. And if I export things into XML, then what happens is the data is specifically formatted and encapsulated in a tagged language so that the resultant computer will actually understand what to do with the data. For this to work, we have to have what's called a document type definition, or a DTD. And it relies on what's called the XML schema. And what this means is that if I take data and I export it from the DB2 server to XML, it's going to be written in a weird format. And the only way that I'm going to be able to get the data into Microsoft SQL Server is to know what the format means for the XML document. So what we're going to do is we're going to use a DTD and an XML schema document to tell Microsoft SQL Server how to get the data in. And then the data is going to be presented through the use of what's called a style sheet. Now, this particular XML document lists fields, and these fields are going to have properties. And you notice it says column width is type 3, here's the value, column order, and so forth. What this is an XML document that has a schema that specifies what exactly the different columns are and what the different fields are that are going to be contained in our XML document. And so what we do is we receive an XML document from the DB2 server, but then we also have to download, usually from the manufacturer's website or whatever system we're exporting the information from, the DTD document, and then that will tell the receiving computer how to process the data. Now, having a database is great, but it has a serious drawback, and that drawback is that it's what's called a point-in-time system. And what that means is that the data that I'm looking at in the database is typically going to be what the value is for a particular field right now. And what I mean by that is, let's say we have a database that has a list of all of our customers and the balances that our customers have for their accounts. So maybe we have a company where we offer credit to customers, and we want to know what the credit is for all of our customers right now. How much money do they have available? I can do that. I can look in the database. But if I want to see the average amount of credit that the users have for the last year, I can't do that out of a database. So we have to go into what's called online transactional processing, or what's called a data warehouse. So it just simply means that we have a database that is responsible for maintaining data over time. So it's data that's formatted a little bit differently. Typically going to be things like I'll have some sort of timestamp, or some of the systems actually create tables based on a date, and then we can use these OLTP systems and then also what's called OLAP to go and get data out of it, and we can perform queries over time. Now the data, they talk about this thing called a star schema, which basically just means that we're going to take all of the data from all of our systems and stick it into one database. And then our database is going to be structurally a little bit different than the actual production database. Because remember, we're using this to get data over time. We're trying to analyze data. Okay, so we're going to use OLAP, Online Analytical Processing, and this is software that's going to allow us to access a data warehouse and actually look at data over time. They start talking about these things called data cubes, which is just simply a way for us to visualize how this works. All right, so essentially think about if I were to have a table that has a list of all of our customers and their balance right now, and I were to make a printout of that piece of paper every day for the last year, then what I can do is I can look down through those pieces of paper, one paper at a time, and figure out let's say I want to look at Bob Smith's account, then what I can do is I can look at Bob Smith on today, and I can plot his credit for today on a graph. And then I go look at Bob Smith yesterday, and I plot the point for yesterday. And I look at Bob Smith 2 days ago, and I keep doing that all the way down through the stack of papers for the last year, and I can get the data over time for Bob. Now, what this does for me is it allows me to look at something that instead of being a point in time, I have a snapshot of the way that his data was every day at the end of the day or whenever we wanted to take it, and we can start looking at the data. So they call this a cube, and essentially what it means is that I can look from one piece of paper down to the next, and we look at the same value for the same cell, the same field for the same record, and then try to look and see what the data was over time. And by doing this, we can go into a process called data mining, which is using this data to look for patterns and trends from the data that's in this warehouse. We cannot do this with the standard database. We have to get into some sort of OLAP system, or just simply even making a new database table that has data that's imported and then putting a timestamp so that way we can look at it. I want to see all the data that occurred on a particular date. Another type of system that we can use is called object-oriented DBMSs, and this is going to be, instead of having records where it looks like an Excel spreadsheet, we're going to look at something that is more like what you experience in a programming class. So now if you've had me for programming classes before, you've experienced object-oriented programming. And in object-oriented programming, I use the example of an index card. And so what I want you to imagine is that we have a blueprint for every one of the index cards. Every index card has a title. Every index card is going to have things like, let's go with an example of automobiles. So if I have an index card for a Ford Focus, then what I'm going to have is an index card with probably like a serial number as the title at the top. And then the index card is going to have things on it like the vehicle identification number. It'll have something like the model, the series, the year, number of doors, number of tires, number of windows, if it's a hatchback or has a trunk, and it'll have all the stuff listed for the car. And so what we can do is each car gets its own index card. Our object-oriented databases also allow one more thing, which is what's called binary large objects, or blobs. And essentially what this is instead of having a field that is either text or a number or something like that, I can actually have an attribute that is a video or a picture or a map. Any type of information that I could get, like a file, could be stored directly in the database. Or it could also be stored externally from the database, meaning I just simply put a link in the database that points to an actual file on the hard drive. So now this is going to be used with applications that are going to be used for much more complex objects and much more complex projects. And once again, if you've had me for a programming class before, you've probably seen this thing called the UML, or Unified Modeling Language. And essentially what it is a way to represent your data graphically. Now this is going to be another modeling technique for your database. So instead of using something like an ERD, we can use UML. And a UML is what's called a class diagram. It's rectangles, similar to the ERDs. And instead of doing things like listing all of our column names, we're going to list the attributes. Okay, so what that means is that at the top here, this is the name of the object, And then this is kind of like a blueprint for each object that we want to create. So in this case, we have an attribute called rep number, and its data type is character 2 digits in length. And then we have a last name, which is character data type 15 characters in length, and so forth. Now, I want to go on a little sidestep here. Character data type is horrible, by the way, because this means it has to be exactly 15 characters long. You want to use a varchar data type. So anyhow, back to the UML. In the UML, we're listing these are all of the attributes. So this is kind of like what we had before with our ERDs. The thing that's different is at the bottom here, you'll notice that we have these things called methods. And what a method is that when we create a new representative here, we can do things like add representatives, we can delete representatives. We actually create in our actual database system some programs, some functions that have to run when things occur. So if we want to add a representative, we have a section of code that does that. If we want to delete a representative, we have a section of code that does that. If we want to change the address, we have a section of code that does that, and so forth. So it's a little bit more than just a database. Now we're getting more into actually programming the database to do things and allow us to have additional functionality. In this lesson, you learned that distributed database is going to allow us to take a single logical database and physically divide it up amongst multiple locations at different places on our network. We're going to allow for location, replication, and fragmentation transparency, which is going to make it where the end user doesn't notice any difference based on where the data is or how it's being accessed. We're typically going to use a client-server architecture, which means that we have a server that processes data sent from our client. We're going to use what's called a 3-tier and server architecture. Once again, that's going to be where we have a web server that is processing a request to generate an HTML document. So the web servers are going to directly interact with web clients, and they're going to send HTML documents. These are going to allow us to make dynamic web pages, not necessarily static ones. This is going to be used mostly for e-commerce. We can use XML to get data from one location to another, but we do need to have our DTD and our schema. We can use a data warehouse, which will allow us to store data for a period over time, which would allow us to create these 3-dimensional cubes, basically meaning that I can drill down through the data and look from one data to the next to be able to do some data mining functions.